The topic of this lecture will be Fischer projections. Fischer projections provide us with another way to draw a three-dimensional molecule on a flat piece of paper. Let's look at an example. This is the structure of S-lactic acid drawn in perspective. For the following discussion, you may find it helpful to make this molecule with your modeling kit. I would recommend pausing the video and doing so now. If we rotate S-lactic acid, we can rotate it into an arrangement so that it looks like this. The chiral carbon is still in the middle, but the carboxylic acid and the methyl are pointing up and down and away from us, and the hydroxyl group and the hydrogen are pointing to the sides and pointing towards us. This is how a Fischer projection shows three dimensions. In a Fischer projection, the chiral carbon is shown as the intersection of two lines, one horizontal and one vertical. And then the groups coming off the chiral carbon are written at the ends of each of those lines. The horizontal lines indicate bonds coming towards us, and the vertical lines indicate bonds going away from us. This is the Fischer projection for S-lactic acid. Again, each point where lines cross indicates a chiral carbon. The horizontal lines are coming out of the page towards us, and the vertical lines are bonds that are going away from us into the page. Because the direction of the lines indicates the direction of the bonds, specifically that horizontal means the bonds are coming towards us and vertical means they're going away from us, there are some rules about how we can manipulate Fischer projections. For example, you can rotate a Fischer projection by 180 degrees without changing the chirality of the center indicated by it. Again, let's look at our S-lactic acid example. If we rotate our Fischer projection by 180 degrees, we get a Fischer projection that looks like this. This is the same compound and has the same stereochemistry as the original compound. If you're not sure about this, pause the video now and make both molecules and convince yourself that they are in fact the same. You cannot, however, rotate a Fischer projection by 90 degrees. Rotating a Fischer projection by 90 degrees changes the stereochemistry of the chiral center. Let's look at an example. Again, we'll start with S-lactic acid. If we rotate our Fischer projection by 90 degrees, we get a structure that looks like this. This is not the same molecule we started with. If you're unsure of this, pause the video and make both of these structures with your modeling kit. Remember that the horizontal lines are bonds that are coming towards us, and the vertical lines are bonds that are going away from us. Let's try to draw this now as well. Here are both molecules written out in perspective. Now let's rotate each of these molecules to point the lowest priority group away from us in order to make it most easy to assign the absolute stereochemistry of each center. Take a moment and assign priorities on each of these structures and determine their absolute stereocenters. Pause the video while you do so. The structure on the left is S-lactic acid. The structure on the right is R-lactic acid. Rotating a Fischer projection by 90 degrees gives us the mirror image of the original chiral center. Another thing you cannot do with a Fischer projection is you cannot flip it over. Flipping it over also changes the stereochemistry of the molecule. Let's look at an example. Again, we'll start with S-lactic acid. If we flip over S-lactic acid, we get this Fischer projection, and this is a different molecule. Again, if you're not convinced of this, pause the video and make both of these molecules. Again, remembering that the horizontal bonds are coming out towards us, and the vertical bonds are going away from us. Now we're going to try to draw these two molecules in perspective so that we can see that they're different. Here are each of these molecules drawn in perspective. Now what we'll try to do is rotate the molecules so it's more easy to see what their absolute stereochemistries are. So I've redrawn both of the molecules on the left and the right in perspective, putting hydrogen, the lowest priority group, away from us. Take a moment, pause the video, and assign priorities to each of these molecules and determine their absolute stereochemistry. Hopefully you've determined that the molecule on the left is S and the molecule on the right is R. Flipping a Fischer projection over, makes it into a different molecule. Again, it turns it into the mirror image of the stereocenter that we started with. Fischer projections make the identification of enantiomers easier. Let's look at some examples. With these two molecules drawn as Fischer projections, it's very easy to see that they are mirror images of one another. Remember that enantiomers are mirror image isomers that are non-superimposable. So what we can do is take one of the structures, for example the structure on the right, I rotate it by 180 degrees to be sure that it's not the same as the structure on the left. Remember that rotating a Fischer projection by 180 degrees does not change the stereochemistry of the center it represents. This structure is also different from the structure on the left, meaning that the structure on the right and the structure on the left are mirror image isomers that are non-superimposable and are chiral. They are enantiomers. Let's look at another example. I've drawn another compound and its mirror image. If we rotate the structure on the right by 180 degrees, we can see that it's now the same as the structure on the left. What that tells us is that these are superimposable mirror images. In other words, they're the same compound. Let's look at one more example. Again, a compound and its mirror image. If we rotate the structure on the right by 180 degrees, we can see that we have a compound that is different than the structure on the left. Again, these are not the same, meaning that they are chiral and they are enantiomers. Fischer Projections are particularly useful for looking at molecules that have more than one chiral atom. Let's look at an example. Pause the video for a moment and name this structure, including the absolute stereochemistry of its centers. Hopefully you've determined that both of these chiral centers are R, and the name of this compound then will be 2R, 3R, 2-bromo-3-chloropentane. When we draw the Fischer projection of a compound that has more than one chiral center, we put the carbon chain vertically, and the IUPAC numbering goes from top to bottom. So, since this compound is numbered starting at the left, our carbon chain will be vertical, and our top carbon will be carbon 1, and our first chiral center will be carbon 2. Carbon 3 will be drawn next, again as a cross of a vertical and a horizontal line to indicate the stereochemistry, followed by carbons 4 and 5, which will be just written in condensed form since there is no chirality to be expressed here. Converting from line angle to Fischer projection is difficult and takes some practice. It can help to make the model and use that to inform your Fischer projection drawings. Take a moment now to make a model of this compound and figure out how we got to this particular Fischer projection. Using Fischer projections to portray molecules that have more than one chiral center makes it very easy to look for planes of symmetry. In this case, it's very easy to see that there is no plane of symmetry, and this molecule is in fact chiral. Let's look at another example. From the line angle, it is hard to tell if this molecule has a plane of symmetry. Let's draw it as a Fischer projection. When drawn as a Fischer projection, it's now very easy to see the internal mirror plane of symmetry that goes right through the middle of this molecule. Because it has a mirror plane of symmetry, this molecule is achiral, and its mirror image will be superimposable. Again, if we rotate the structure on the right by 180 degrees, we don't change any of the chiral centers, and so it will be the same molecule. This rotated molecule matches the structure on the left, indicating that these are the same compound,